demonstration is Active Noise Control System for Ground Vehicles. The company will have 20 minutes to demonstrate their technology, followed by a 10-minute Q&A session. And when you're ready to begin, we will start the clock.
All right, good morning. I'm Greg Kangas.
I'm Kevin Nelson.
So yeah, Great Lakes Sound Vibration. We're here to show you guys some technology, active noise control, as applied to what our demonstrator is. It's essentially an enclosure for a genset, 5 kilowatt genset. There's not an engine running inside because we're indoors, but we do have an engine simulator, basically a speaker that we can generate noise with, and we want to show basically the capabilities of our control system, how the algorithms work, and then start some dialogue of where can this be applied outside maybe this application specifically, or outside as we discuss the the strengths of the algorithms, where can this be applied elsewhere. We have some ideas. We'd love to hear some ideas from you as well. So with that, we'll step through some slides here quick, and then we'll get the demonstration going, and we'll try to get as interactive as possible because we want to put it to test here and see what you think. All right, so a few points about active noise control and in general for noise management inside of the military and ground vehicle sector. We're focused on next generation combat vehicle as an area of potential use here. So one thing we found doing a lot of development with prime contractors of ground vehicles is kind of our background in noise and vibration is the noise issue always comes down to how much available space is there. And when you talk low frequencies, long detection distances, the space required to attenuate noise from a vehicle gets larger and larger because of the nature of the low frequency noise waves. And this is where we're trying to address that performance issue with active. It's focused more on a tight spectrum rather than a broad spectrum application like conventional noise control treatment. Also for noise control for ground vehicles, vehicle architecture is tough to change late in the development cycle. So we've been, on that team several times through GCV, FCS, and playing that role of helping the noise signatures on the vehicles. And what happens is it's a lower priority in the grand scheme of things, and noise control comes after all the other stuff works, is kind of how we see it. By that time, you need to change the architecture of the vehicle. It's a little bit too late, and you start relying on, well, there's no space left, but we have this low frequency issue. So being able to bring in a solution towards the end, we'd love to affect the vehicle architecture. That's kind of how we would approach ideally, but in the case where you can't do that, we would love to come in with another solution that's a lot more compact and focuses directly on the spectrum of interest. And then the third point, this is an adaptive system, meaning it can be applied, it can be calibrated to the whatever the situation is. So the NRE, non-recurring engineering time, goes down considerably. So one point on active noise control, we want to provide this noise control efficiently, and the keyword efficiently we'll talk about a little more, but we can focus in on precisely where's the noise coming from an engine, an exhaust case like this, simulator. Just only attenuate the frequencies that we care about and track them, instead of casting a broad net over all the frequencies, and also that's the volume you need to do that as well is often too much. So a couple diagrams here of how this system, the base architecture can be applied throughout the vehicle. A common controller could control something from the exhaust pipe, from the intake, something from the cooling fans, inlets, outlets, anywhere where there's penetrations where flow has to move. This does not impede the performance of the fan or the engine. It's just basically absorbing the sound waves only before the energy passes out the tailpipe or out the outlet or even inlet. The architecture in general is, in a simplified version, is using common controller, common set of amplifiers, or an amplifier with multiple outputs, and controlling more than one component on a vehicle to get system level performance. So a little bit on where this could be applicable to an engine application on an exhaust pipe, say. You see the green plot is these tonal peaks that are always there from a diesel engine, especially in an exhaust pipe. What we try to do, conventional treatment will try to take a broad spectrum. This is a little bit exaggerated, but that's basically how it works for conventional treatment. You get these broad spectrums because when the RPMs move, you have to carry through all that. Now let's think about power density, sound power density. When we look at the next slide, the active treatment focuses on just the areas of the spectrum that are needed to be focused on, and that's where we get something huge to cast the broad net down to something small like a 8-inch speaker or something. That's kind of the main benefit we see of being smart about where we attenuate. Let's find those frequencies and track them and take them out. So I guess this is probably the last slide here, and then we want to get into demonstration. And really, it was a study done on a 2.5 liter turbo diesel. This is an engine utilized for GMV size vehicles, and we put it on a dyno. We did some characterization and did some rough numbers and tried to compare it to a conventional noise treatment 1, which is let's get the same amount of benefit acoustically, and let's look at the costs. And then also treatment 2, where let's keep the costs about the same as what we think active noise will be in production, and let's see what the benefit is acoustically. And the results are just trying to show, again, it's an efficient system and it's high performance. So with that, let's kick it into let's get the demonstrator going. So what you see here is, again, this is I'll step over here. Is this mic on? So this is basically an enclosure for a 5 kilowatt generator. It's used in the marine industry. I think at one point I talked to the supplier of this shell here, and they were thinking about putting on back of M-Razors with the genset. Anyway, it's a noise enclosure, but what we're trying to highlight here is if you give it a tailpipe, it has to communicate with the environment because it needs to breathe, it needs to exhaust. And we'll show here, we just have a speaker set up to play some fake engine noise, and then we have a speaker teed in, just like you saw in the drawings, and it's trying to absorb that energy before it comes out. We'll just try to, we'll put it going and see what happens here. So.
Okay, so the first step in installing active noise cancellation on a vehicle is to characterize the system for that vehicle. So that involves essentially playing white noise through the system and then measuring the characteristics of that noise. So we'll run a demonstration of that right now. It's going to be a little noisy, just so that you guys are forewarned. So,
And this step, just to highlight, this step happens once per application. So it's like in the shop. once per application, and once it's characterized, it's good to go. It can operate at a wide range of RPMs, things like that.
Sorry, I had it plugged into the wrong port.
So another part that you saw that we haven't rehearsed as well is the NASCAR speed of setting this whole setup up. It's usually sitting in a lab, ready to roll, and yeah, we get to set it all up in front of you guys.
So it's currently running through its characterization cycle. I'm not going to plug it in until it's finished.
So is it playing white noise?
Yeah, but it's out, you know. So it would typically run for about 30 seconds. So if you have more stuff you want to talk about.
Okay, is the white noise gonna come on while we're?
No, I need to. It needs to finish its cycle. Then I'll plug it in. Then we'll run it.
So yeah, it's setting up right now. But essentially, the very first step, play white noise, which is like, if, static on a television, that noise, and it'll get the transfer functions needed to basically track wherever this RPM may go. So
sorry about that, guys. Let's try this one more time. There it goes. Oh, shit. It's set up wrong. That's why it's taking so long.
all right, so is it gonna stop? Is it still going good?
Yeah. I'll need to do it once more. Sorry.
Okay, can you stop this? Or how long is it gonna
I
go?
can't stop it.
Huh?
I can't stop it.
You can't stop it. Okay, so we'll just listen to the white noise for a while here. That was a characterization that was about 10 times longer than we normally do.
Yeah, I've got my settings wrong here. So, yeah, you can see it's captured the phase characteristic there in the coherence of the system, which looks good it looks exactly like how you'd expect it to.
So you gonna run another one, or you gonna?
Yeah, I'm sorry. I
Okay,
had my settings
we'll run a
wrong.
shorter one now. Now our ears are tuned into it. And again, this is take it out of the box, hook it up. This is what you do one time, and then it's good for its lifetime, essentially.
There it goes. Okay.
Okay, so it's characterized. We see good coherence. Scroll down a little bit. Good coherence meaning that we're ready to basically cancel the noise. So
So this is what the technician would look at to understand that the system was installed correctly.
all right, now we're gonna play some fake engine noise. So we just turned on a couple harmonics, and let's just assume this is engine. Now we'll work through the cancellation.
So I will bring up a
So the plot you see is an acquisition system hooked up just to read the microphone.
ooh. the resolution set up wrong on this.
Okay. So in order to show, we're going to show high resolution, which right now looks a little blocky. But the idea is to show with the plot that I showed earlier, where there's tonal peaks within the spectrum that are created by the engine, and we want to show how to cancel those in real time, and then we'll also show how they track with RPM.
That looks better.
Okay. So the plot. There we go. That looks more closer to an engine noise spectrum from about 0 to 1,000 hertz.
As you can see, a lot of tonal components in the system. This is something that's very typical of engine noise. Although there'd be more broadband frequencies in a regular noise spectrum. This is just mainly for demonstration purposes.
So I think we chose about 6 or 7 harmonics. So 6 or 7 of those peaks to attenuate. So go ahead and cancel.
Okay.
So you see all the peaks drop way down. I think we left one. Maybe you can turn the cancellation system off again, and the noise comes back.
You can
So
see.
that's it in a nutshell. Very basic. Now to get further along here, it's like, okay, well you could tune a system mechanically to do that. But what about tracking it in frequencies? You know, RPM changes. Gensets maybe, maybe not, but an engine on a vehicle for sure. So do it again, and we'll simulate the noise and watch how it tracks.
It's difficult to hear now with the. So basically, I've brought the speed of the vehicle up. So I'll turn the system off now, and I'll bring it back down, and you can hear it move.
So that's with it off. You see all the tonal noise is still there. It tracks the frequency. I don't know. That shows essentially what we're talking about here. It can track with the speeds. We tried to tune it where it can track with the speeds similar to how an engine under load would go up and down, and it checks out, the numbers check out. I think what we want to do now, we have a couple minutes before our discussion. We just want to go and just try a few other things.
Well, the last 10 minutes are for discussion, right?
10 minutes. We got 2.5 minutes to play a few other things, and I'd say first thing, maybe turn the volume up, or do you want to keep the volume down still?
We can turn it up a
We
little.
want to show a little bit. We want to just stick our necks out there and just show a little bit of what may or may not happen when this thing gets put out in the field. Because risk mitigation. If this thing starts barking, now your detection went way up. And we've been playing with the code for a while, but we like to put it to test. And there's risks to be had and to be mitigated. But we just want to play with it a little more, just to show some more capabilities. All right, so he's adding in a few other things, make the noise sound a little different.
So we'll try a higher order tone, which would be or a higher frequency tone, which is something that you would see like in a fan.
Fan noise.
Maybe bring that down. It's annoying. So I'll configure the system to look for those two tones.
Hopefully your ears are getting annoyed by now.
Nope. Yeah. See if that one works.
Just keep them the same. Go for both of them.
So it actually works on higher frequencies too, which is
The RPM. Not that fan. Variable fans.
that sounds a little.
So you see the higher frequency, a little slower to track, which means the parameters will need to be updated, need to be changed, and that's all part of processing speed. Those can be actually tuned to a system. So if you have one tone like that, the CPU available to do the cancellation, you can actually make it update faster and actually track that faster if you wanted to. So there's all these parameters that can be customized to the system. And really we tune the parameters of the algorithm for a low frequency application, but it can be applied to the high frequency and basically go for a wide range of frequencies. Our hardware we've estimated to go right through the whole right through the human hearing spectrum. We've only tested up to thousands of hertz, maybe 1,000 hertz. So, but we're actively pursuing, working through some development for the high frequency stuff, and other efforts currently. So, which will just only add to this. Anyway, that's it. We're looking for feedback. Think of this in terms of a system like this with speakers. Also, we just saw something come through the .c, looking for a UAV that's doing shot localization that wants to hear better. And there's a lot of noise involved with the UAV itself. We proposed a white paper just recently to take the self noise from the audio stream, because you know about it, because you have a reference, just like this. We have a reference to the TAC. You have a reference to the vehicle. You can take that noise away from the signal, and now your shot localization becomes a lot more clear. And that's just another application that wouldn't require no hardware, like speakers, just the software. And that might be a good spot for us to start. We're looking for other ideas. So anyway, let's go to questions. Go ahead. Need the mic?
So, anytime I've been around a track vehicle, with respect to a track vehicle, I mean, I can always hear it before I see it, right, a long way off. I think the engine's a big source of noise, but so are the tracks. Have you ever tried to do any kind of cancellation of that kind of external uncontained noise? It doesn't have a nice exhaust pipe.
Yeah, right. So one thing with active cancellation is you need to contain the noise source. Exactly like you said, an exhaust pipe that's condensed. For track, we're working on other R&D throughout the Army, I think the Marine Corps actually. It's a different problem. It's structure borne, it's impact, and there's a way to isolate that and dampen it. However, you can think of it more as a vibration, or originating the structure borne, the vibration side of the problem, and the structural, which we haven't brought active to that, but I would only see something that in terms of controlling the vibration, the structure borne, and all that.
Yeah, so this particular technology is much better suited for their vehicles that are kind of covered except for ported outlets where fan exhaust or vehicle intake air, vehicle exhaust air goes, and it's difficult to treat those to over a wide operating range of the vehicles. So this technology is better suited for that.
Have you tried to track or do a correlation between the level of noise attenuation and the distance by which that can be heard?
Yeah.
So,
Yeah, we've done some of that just using some like mil standard 1474, and yeah, I mean it drops it in half in some cases. Some cases more. It depends how dominant the low frequency or the tonal frequency is. But yeah, we have done that. Considerable drop.
and in terms of calibration, do you calibrate for a specific frequency range, or can it be?
Yep.
calibrated
For this one, we did up to 1,000 hertz.
Okay. And how often do you have to do the recalibration?
Just once.
Okay.
Once per application.
So on the battlefield, there's obviously non-cyclical events that happen, within the vehicle. Are you able to, anticipate those in some type of method to dampen them?
Yeah, so there are technologies that are better suited for non-cyclical events like you're talking about, and we're implementing them in the controller right now. It's an area of active interest for us. But this particular controller was designed specifically to reduce cyclical tonal noise that's, propagating out of.
Referring to like wind noise and tire noise and things like that? Yep, it's exactly, we're working with NASA to do broadband noise cancellation, which when you add it to this control system, you'll get the tonal peaks you saw, but you also see the broadband, which is a really big issue when you start thinking UAVs. The item I talked about, UAVs, it covers the spectrum that you're listening in for shot localization. How do you get that noise out? Well, as long as it's coherent with something on board, which it usually is, even flow noise and tire noise and things like that, you can take it out of the signal and you can localize again where you couldn't before or farther out, you know.
That being said, the best application for this is for low frequency noises, which are otherwise very hard to treat, as the engine moves in operating condition, right?
But it's highly applicable to broadband, like wind noise and things like that.
Are you guys dependent on the speaker location once the vehicle is characterized? Say, hey, we want you to put this on Bradley, and you say you need X feet from the manifold or something like that. Right? Do you have that
Great.
flexibility to say if they only give you this
Great
real
point.
estate?
So there's one, pretty much we could put it anywhere, but there's one check where if you do a two-speaker system offset, because there's usually one frequency that you can't really get to because of the length effects of where that is in respect to the outlet. However, if you have two speakers offset, you're good to go. And it's really tight on the low frequencies. It's, if you can get out of that region with one of the two speakers, you're good to go.
So we've run this setup on we've run this technology on several setups in our lab and also on two different vehicle
LT, ATV,
demonstrations.
GMV.
Yeah, and we had a wide range of real estate available to us on those vehicles. We were able to adapt it perfectly fine on
The
each
M1
case.
APU is the original one that we started on.
I'm going to go in a completely different realm. So, what is the actual device that's doing
It's a speaker.
just a speaker?
Uses noise to reduce noise.
Scalability of that speaker?
Scalability meaning,
How small can you get it?
okay, small.
So I'm going to look in a whole different aspect of, can
Like-
you get it small enough that a person could carry it on their body?
Yeah, it's all, this is a 6-inch speaker.
Yeah, the system's already light enough to be carried. The actual device in
This
here.
is a generator simulation.
So if we can get a power source small enough to do that speaker, could you drown out the noise of a person?
So
So I have a team of 6 and they all carry one on their body. They're calling back and forth to each other through a radio, through a mic. Could they cancel out the noise so that nothing really comes out past them, almost like a bubble?
yeah, you can't, yeah.
So we've done.
That's where I could see that this being used.
This can create the sound bubble coming in, so you want to be quiet. An operator needs quiet, but he can't wear a headset or something. You can use that. You put microphones near the ear. It creates a sound bubble from coming in. It basically uses the speakers wherever they are, and that's what they do in automotive. It's the same concept. However,
Not in a
stopping
headset, but more on,
it from going out,
yeah.
that's not an application. That's you're getting outside the box. Great question. It could, yeah, maybe I don't know.
I have to think about it for
It's
like that.
something we've never thought about.
Other applications that
Yeah.
I like it. Hey, well, we'll think about it.
Have you characterized, you said some military engine, I didn't catch which ones, but like a Bradley
Yeah,
has a pretty loud exhaust.
Yeah.
right.
So this demonstration is mainly about the how the algorithm works, right? Like the actual
They want size up or
yeah, the
something?
actuator
Size up
can
to
be, if you need a loud engine, you typically need a larger speaker and a larger power
So I'll
source.
say something like this: if you want to get a really low non-detectability limit on a Bradley, you start looking at the frequency ranges you have to attenuate. The size of silencer, we develop silencers and mufflers for a living. It would fill up this table. That's the size of volume you have to do. When you look down and say, I just need this part of the spectrum, if I could take that out, it's gone. Now you're down to a speaker, a set of speakers that are a lot more manageable, and you can place them in a lot different spaces.
Have you characterized the durability of those speakers? So
When
that-
you're- we were gonna
did
get the
one
look-
case,
yeah.
we put it on a dyno for a 120-hour NATO cycle, and And with it, just using a conventional speaker, we have other designs of like stainless steel speakers, but this is conventional and it survived through that. We'd love to try an application of interest
Yeah.
beyond.
So something
scale up.
surprising we found is that if the speaker was in an enclosed environment so that no air could escape past it, could just generate sound, right? Then this, even being offset from the engine, it really didn't see large temperature swings. It was actually like a very livable environment.
Seal from the flow, it doesn't flow down.
Yeah.
That's good.
So we-
Isolated.
Yeah, we have a couple hundred hours running in an engine without too much difficulty.
So any more questions? We'll be here most of the day, so thanks a lot.
Yeah,
and we'll
yep.
do the innovative
And
score
we'll be able to play with this a little more.
We're gonna have it set up on a table for anyone to play with that wants to.